Yeah, so I'm Peter. I'm working on the RAPIDS team, and today we're going to talk about UCX-Py. Matt Baker is also going to talk a little bit about that. We also have Ben Zaitlen on the call, but I think he will not be presenting today. Um, okay. So UCX-Py, what is UCX-Py? It's basically a Pythonic interface for UCX. And by that, I mean that it's easy to get started for Python developers. So there are some, let's say, some differences in languages from C, C++ to Python, and UCX-Py aims to implement what Python developers are normally expecting to see. And it's also a simple replacement for existing communications. So a lot of Python developers will be already familiar with Python sockets. And so it's meant as a simple replacement for that. It's easy to just plug and play. Well, it's not exactly plug and play, but it's very close to that. So as I mentioned, it's for Python developers, and Python developers in many cases are not expected to have any knowledge of low-level communications, UCX or C. So in that case, UCX-Py is not also expecting Python developers to have any of such knowledge. All they need to know is a little bit about how to send and receive buffers and Python knowledge, of course, a little bit of Python communications, but that's all. And today, I think the biggest users or indirect users of UCX-Py are data scientists. And they're not expected to use UCX-Py directly, but through applications such as Dask. I'll go into a bit more details about Dask later. So the primary use today is in PyData. Briefly speaking, PyData is what is the data processing and machine learning ecosystem of Python called. It comprises of several different libraries and different data structures. So for people who are familiar with a little bit of Python, they probably know about NumPy. So once you know about NumPy, you know that NumPy is mostly working on arrays. And then we have data frames, which is sort of a columnar table or database kind of format. And this is provided usually by a library called pandas. And then you have machine learning libraries such as scikit-learn or distributed computing in Dask distributed. And as I mentioned before, I'm part of the RAPIDS team. And what RAPIDS is doing is basically porting all of these PyData ecosystem to run on the GPU. So we have libraries for processing arrays, processing data frames, to do machine learning, to do distributed computing, but all on the GPU. This is what the ecosystem is usually expected to interact with. So if we have RAPIDS here in the center, RAPIDS can interact with all these libraries: PyTorch, MPI4Py, Numba, CuPy, Chainer, MXNet, and others. And this is possible by using some community protocols called CUDA Array interface and DLPack. So both of these protocols allow us to move data back and forth without any copying, so a zero copying format, which allows us to interact efficiently with all these libraries without copying data over and over again. And we, of course, then can plug in UCX into all of that and pretty much speed up all the communication when it's necessary between GPUs, between hosts, or between InfiniBand devices, etc. Using UCX-Py is very straightforward for Python developers. I think most C++ people will not be familiar with CUDA, but sorry, not CUDA, but Conda. But Conda is some sort of package manager for Python, and you can pretty much just install all the packages, the CUDA toolkit, the UCX, pre-built UCX and UCX-Py, all with a simple command like this, with or without CUDA support. And this allows Python users to just go there and start using UCX-Py without having to build everything from source. I know most people using UCX are commonly building from C source code, but this is not the case for Python users. They're in most cases, they're not expected or knowledgeable to build everything from source. So we have to provide packages that they can just install on their machines and get started with. But it's of course still possible to build everything from source. We have instructions for that in the UCX-Py docs, and I'll mention a little bit later, but current Conda packages don't support InfiniBand because of MOFED compatibility. UCX-Py is supporting mainly two use cases. Pure Python, so that means that the users can just install UCX-Py and start sending in buffers back and forth. And with RAPIDS and Dask CUDA. I'll go over each of these cases now. Here is all the Python API, let's say the public API that the users are expected to interact with. In most cases, they're only going to use a very small subset of these. For instance, create listener, create endpoint, and send and receive on the endpoints, and listener, close, and all these very high level functions or methods. And the expected Python usage is supposed to look something like this. So roughly speaking, what we want users to do is they have a buffer that can implement, for example, the array interface or CUDA array interface. As I mentioned before, CUDA array interface is just one protocol, and that's based on the array interface protocol. Obviously, the array interface protocol predates CUDA array interface, and it's a host interface. And CUDA array interface is a device or GPU interface. And both of these interfaces allow transferring zero copy data through some kind of Python metadata with the pointer contained within, and other information such as shape and strides and so on. And once the user has a buffer like this, you can, like a message, you will just have an await EP send message on one side and EP receive message on the other side. So that is pretty much all the user is expected to know about. And I know for C++ developers or C developers, this may not be the most expected interface. In Python, we have this kind of async functions that have asynchronous functions that we can use an await statement to wait on the completion of that before moving in. So it's just very much of an asynchronous kind of interface, but it's very widely used in Python. So a complete set of code using CuPy. CuPy is pretty much just a rewrite of NumPy, but for CUDA. And you can just plug and play NumPy and replace NumPy by CuPy, and you have pretty much the same interface. Of course, there are some limitations. CuPy doesn't implement the entire NumPy API, but it implements a very large chunk of it. And on the left side, we have a server, and on the right side, we have a client. So The user is expected to just create a listener and await until it's closed. And on the listener, it will just comprise all the communication part of it. Can you see my mouse, by the way, or not really?
Yes, we can.
Perfect. Okay, so once you create the listener and you then await on the listener to be closed, and here you will just create some empty buffer and await on receiving some data from the client, and then check the data and send some other information and close. So this is pretty much all the user needs to do on the server side. On the client side is something very similar. It will, the user will just create an endpoint and connect to the listener on the other side, and basically just send and receive a message and close the endpoint in the end. So that is pretty much everything the user needs to know to be able to plug UCX-Py in his application, which is very simple and very straightforward for most Python developers. This would not be a problem, as opposed to just implementing everything with UCX that would, pure UCX, I mean, that would require a much more in-depth knowledge to get started with. Now I'll talk a little bit about Dask. Dask is just a Python library for parallelism. It allows you to scale libraries such as NumPy, Panda, scikit-learn, and others. And this is the core of RAPIDS parallelism today. It's flexible to build complex and custom systems, and it's very accessible for beginners. It's also secure and trusted for institutions. And on the Dask side, for people who are familiar with the Python ecosystem, it's very straightforward as well. So normally you would have, for example, a NumPy array, and Dask is simply a cluster of those arrays. So instead of having one NumPy array, Dask will have various NumPy arrays, and the interface, its API is virtually the same as NumPy. So everyone who's familiar with NumPy will have no problems in scaling with Dask. The same for Pandas. A Pandas data frame is, a Dask data frame is just a cluster of Pandas data frames. And you can also use a DaskML library that is a rewrite of scikit-learn or part of scikit-learn to do some machine learning on these buffers, on these data frames or arrays. And of course, Dask is mostly host computing only, so CPU only. But with Dask CUDA, we can extend this with RAPIDS and do all this processing that it's possible to do on the CPU. We can do on the GPU with RAPIDS libraries. Dask is a task graph execution library. So this is pretty much the kind of task stream that it will create for the user when doing, for example, a cross-validation grid search on a scikit-learn, using scikit-learn, or not using scikit-learn, but using the scikit-learn API with the DaskML library. And the user is able to see this in real time when Dask is processing. So you can just go and see the Dask interface. The dashboard has a lot of this kind of nice graphs, not just for these, also for communication. We'll have an example later on, but for data scientists, this is very useful and helpful to understand what is going on. But I know that most low-level people don't care about this. So, but nevertheless, it's useful for data scientists mostly. To use UCX-Py with RAPIDS and Dask CUDA, it's very straightforward. So I don't want to go into all the details, but with Dask, you have a local cluster, and with Dask CUDA, you have a local CUDA cluster here. And the only difference is that when we want to use UCX-Py, we'll change the protocol, which defaults to TCP to UCX. We also today have to enable the different transports by hand because, for example, one of the limitations that we have if we don't do this today is with a DGX2, something that has been discussed earlier today, that we have too many transports, so we have to basically limit all the transports that we're using, otherwise we'll have issues with UCX. And this is more intended for data scientists, but this is pretty much how a simple data frame processing on the GPU would work. So you have two Dask QDF data frames. So they are both contained in multiple smaller QDF data frames, and they can be split on multiple GPUs and multiple nodes. And then you do a merge on that array, or sorry, that data frame, and you get some results from it. So it's this simple. The user has to just create his cluster and do some processing. That's all that needs to be done to use Dask with UCX-Py. Since UCF 2019, we've had 6 or 7 releases, almost cutting the 7th release since then. This should be out in, I think, 2 or 3 weeks from today. And here's a list of all the things that have changed since. We have a substantial increase in documentation that has been very important for users. In 2019, we didn't have so many users, but now we are getting more and more users asking for questions, and a big part of that is now in the documentation, so it's easier for people to get started with. API improvements and extensions, support for user-specified tags, endpoint reuse. So this is a class that we created because of an issue with CUDA IPC Open Mem handle that wouldn't allow us to map the same CUDA device buffer twice or more than 2 times. And this is something that will probably be deprecated because we now have a fix. I think I'm not sure if it's already been merged or will be merged by 1.10. We are also separating the Python API from the Zaitlen backend. To give a bit of context, Zaitlen is just a kind of, it's a library that translates Python code into C code, and thus it makes things much faster than just using the Python, basically the Python interface to do everything on time, just like a scripting language. But Zaitlen will convert that code into C++ before, so it requires a compilation step. It's not just an interpreted part of language. And we did a lot of improvements on the Zaitlen code to reduce the Python overhead. We reduced also the hard-coded UCX variables to rely more on UCX defaults. So I think that simplifies as well the maintenance for us, and perhaps for users as well, that they don't need to find out what has been hard-coded, although we have a few things still hard-coded, such as the mem type cache that we discussed briefly earlier today as well. We had many bug fixes. So by the end of 2019, we rewrote the UCX-Py bindings to use more of these asynchronous type of implementation. And since then, we found several issues with seg faults, deadlock, and cleanup issues. So this has been mostly a fixing year for UCX-Py. We now have it in a very stable state. We don't know of many hanging issues anymore, which is great. We have better error handling and support for endpoint error handler. The logger formatting now looks similar to UCX. So that simplifies things when you want to have both UCX and UCX-Py logging, and parse this logging visually is much easier now. We added NVTX annotations, more benchmarks, and multi-GPU and multi-node tests. And these have improved our lives incredibly, because by the end of 2019, we didn't have so many of those benchmarks or tests that it was very difficult to catch bugs, but now it's much easier today. This is more or less how the NVTX annotations look like. So for people who are not familiar with NVTX, NVTX is a library that allows you to annotate when a piece of code is running. For instance, we can annotate when UCX-Py progress is being called. So we add an annotation at the beginning and at the end of the function. And once we profile that code, we can see exactly when UCX-Py progress was running. And once again here, and we have more annotations for also send and receive. And perhaps this is something that we still can improve further, but it has provided us with very important information when we were benchmarking for slow transfers. And this is something that you can just profile your application with NVIDIA Insight systems, and the profile will automatically include those annotations in. So when you zoom into the code, you'll see that those annotations are there. Testing and benchmarking, as I mentioned, has been improved quite substantially. So today we have some code that is running on some of our clusters, and this in particular is a QDF merge throughput measurement. So we can see, if I'm not mistaken, this is running on 8 CUDA devices with CUDA IPC and InfiniBand both turned on, and we see that the throughput for that particular workflow is around 20 gigabyte per second. We have also on the right side the historical throughput that we run nightly, and this helps us to catch potential regressions. These are some of the benchmarks also with the QDF merge. This was running on DGX1 with, in this particular test, we were running only with 2 GPUs and 100 million rows per chunk on a data frame. And as we see on the left, the bandwidth we get with Python sockets or TCP is just around 400 megabytes per second. But once we move to CUDA IPC, we see around 40 gigabyte, where the theoretical maximum should be around 50. So it's still not perfect, but we are very, very close to what we would get with UCX. Here the same, still on the left, the same 400 megabytes per second. And with InfiniBand, we are getting 9 out of 10 for the theoretical maximum in this machine. Talking a little bit about the internals of UCX-Py. UCX-Py is currently divided into 3 layers. The Python layer, which is what the user sees. This is pretty much the API that I have shown earlier in the presentation. The Zaitlen layer, where Python interacts with C. So that's where all the UCX interaction is happening. So to put it in a more concrete kind of example, this is where we have UCP tag send and receive and so on. And we have also a C layer, which is a very minimal layer, which is just comprised of some parts of the codes that are cleaner to write in C than Zaitlen, although we could still move that to Zaitlen. and some parts of code that interacts with other libraries, such as HWLock. So today we have only a topological distance calculation there in C, but since there is some effort on UCX to bring that to life directly there, we will probably eventually deprecate these and just rely on the pure UCX implementation. We have also an array data type in UCX-Py. This is a class that is also implemented in Zaitlen to get most of the performance we can. It emulates the NumPy ND array class. And by that, I mean that it implements pretty much all the same attributes, such as shape, strides, data type, and so on. It's compliant with the protocols that I mentioned before, array interface, good array interface, and therefore it makes it easier to interface with PyData libraries implementing those protocols, such as NumPy, CuPy, and Numba that I mentioned also before. And because it's written in Zaitlen and it's very minimal, the interface of array is very minimal, it's also efficient to interface PyData and UCX. Some of the use cases that we have with UCX-Py are comprise RAPIDS TPC-XBB. So TPC-XBB is actually a benchmark that is publicly available, and many manufacturers just use this as a benchmark for machine learning and ETL workflows. It comprises of 30 big data analytics queries, and the RAPIDS team has benchmarked on the 1 terabyte and 10 terabyte scales. To achieve that, we use a lot of different libraries, and these are some of the libraries. And of course, to mention one of them is UCX at the end. This is more or less what we achieved with RAPIDS on TPC-XBB. The blue is the RAPIDS time to run all the 30 queries, and the red was the current TPC-XBB leader as of June 2020. I haven't checked if this has changed since, but RAPIDS has decreased quite substantially the runtime, and it's possible to do that for the 1 terabyte and 10 terabyte scales. And this is where the interesting part is. This is the Dask task stream. It's part of the Dask dashboard that I mentioned before. So this is what you see also in real time when Dask is processing. And all the blue and green tasks are all compute tasks, different compute tasks, but the red part is communication. And on the left side, we see that is with Python sockets. And on the right side is with UCX. So we decreased by the total runtime by, if I recall correctly, this was about a 2x speed up, or maybe even more than that, just by introducing UCX-Py. So that change that I mentioned before, pretty much replacing protocol from TCP to UCX, you get all these for free, all these speed up for free. Another very important and exciting use case that we have is on the Summit, the ORNL supercomputer, on research for COVID-19. So this research is a structure-based drug discovered workflow, and it achieved a total speed up of 52x when comparing 6 GPUs versus the 42 CPU cores on each node. So this is the speed up for a single node, and UCX is responsible for about 2x of that speed up versus the Python sockets. So Summit is comprised of 4,608 nodes, and with 6 GPUs per node, so a total of more than 27,000 GPUs. And this is all interconnected with Mellanox and InfiniBand. And so UCX-Py plays a very important role there in allowing data scientists to quickly run all their workflows on Summit and with a very easy process for scaling up their work to more nodes because of Dask. So this is more or less how the workflow looks like. On the left, we have Jupyter, and Jupyter is just a very interactive user interface that allows data scientists to quickly test and modify their running code. And that interface is connected to Dask, and Dask is using UCX-Py on the backend for all the communication. And finally, Dask is basically scheduling work on Blazing SQL. We'll have a talk, I believe, on day 3 about Blazing SQL. So there will be much more details there. And also with RAPIDS for data analytics, machine learning, and visualization. And this is generating over 1.3 terabytes of data on that COVID-19 workflow. Some of the UCX-Py challenges are support for UCX conda packages with InfiniBand and conda packages supporting for every transport. So this is something that we discussed with Mellanox folks earlier this year. And the problem with that is that InfiniBand with MoFad is actually not forward nor backwards compatible, and providing conda packages for all versions of MoFad is not feasible for us. So that means that we could only provide a few of them, and then users would have a different version and wouldn't be able to use it properly. Or I think this is something that we still have to discuss, but apparently MoFad 5 and above will be backwards compatible. So we could eventually just start building against a single version of MoFad, and that would solve all our issues. But that's still something that we have to discuss further. UCX-Py today is only single-threaded. So there was one of our use cases was to use Blazing SQL, but Blazing SQL requires multiple thread communication. So because of the UCX-Py internal state, this isn't safe, and there were some problems there. So one of our goals is to add multi-threading support for UCX-Py as well. Shared memory support, I think I tested this in 1.9 and this was fine, but I have to double check. We are still only providing conda packages for UCX 1.8, which is something that we intend to change soon. We want to have on the next couple of weeks UCX 1.9 build for conda packages as well. And further latency reduction, we did a lot of improvements on the Zaitlen API, but there's still more room for improvement there. And on the UCX, what we would really like to see is UVM, CUDA UVM support. I think there's some work ongoing in there, but this is something that probably the #1 feature that is asked by Dask users and UCX-Py users in general, because today we cannot enable managed memory because of the lack of UVM support in UCX. We are still in the process of working on UCX-Py to upstreaming it to the OpenUCX org. We did a lot of separation of the API and the Zaitlen backend. The plan was to actually get it upstream to the OpenUCX organization in 2020, but because of the crazy year, we unfortunately got delayed to early 2021. And our plan is to upstream it in 6 phases, perhaps more, just to simplify reviews. So the current UCX-Py code, I think it's around 4,000 lines, and probably a single PR would not be very welcome. So we want to do it in steps and start upstreaming piece by piece, so to reduce the burden on reviewers reviewing that, but this is something that we intend to do early in 2021. And the 6 phases are basically to upstream the C backend, the Zaitlen backend, both API and code separately, the front end, the Python code, API and code also separately, and finally the Python packaging mechanism that is required. And yeah, and we intend to start this early 2021. And now I'll hand it over to Matt Baker. He's going to talk a little bit about the UCX-Py and the future of HPCs, more specifically on Summit. Please, Matt, go ahead.
Okay,
Oops,
so we'll preview the next slide. So,
yeah, sorry about that.
So I'm Matthew Baker. I am with the, what are we calling it these days? Intelligent Systems and Facilities Group at Oak Ridge. So, been involved in UCX for a little while. And so I've had an interesting experience going from developing on the bottom end of UCX to developing runtimes and other fun goodies on top of UCX. And so wanted to share some of my experiences about where things are and where things are going with especially with the Python interface. Because these supercomputers keep on getting more and more complicated and far more sophisticated. Gone are the days of Jaguar just being a massive Octeron cluster. As described, Summit has, many nodes, but they are also fat nodes with attached accelerators, making the memory space very interesting. And the next generation machines are going to get even more interesting, with the smart NICs that were brought up earlier. And so, since these machines are not getting less complicated, but in addition to that fact, the use cases are getting more complicated. Peter did a good job summarizing the COVID-19 workflow that was developed. And this is going to be a continuing trend where the data scientists want to have a fully integrated workflow that handles file and memory management efficiently. Okay, so next slide. So, in this, we had a lot of success in scaling up. And we powered through a few complications and managed to get excellent scale up and scale out performance, with most problems being caused by a misconfigured environment rather than UCX code base itself. Now, another tremendous success for UCX in this application is the fact that this workflow was able to be stood up and scaled out in a matter of months, where historically DOE applications and tools and workflows go on a many-year timescale. Part of the success of this came from the fact that these tools, with their backend in UCX, has been in terms of being able to do performance portability, where codes developed on a DGX box or a local workstation can then be taken to these large supercomputers and scaled out, and done so in a very efficient way. So, what's going to be the next generation that drives the increased performance? Next slide. So this opens up questions about using UCX to help with the I/O problems. One of the biggest challenges of this, the workflow, was just purely the fact that you're managing 1.6 billion files. And so that's not going to be handled well by distributed file systems such as Lustre or GPFS. So that comes to the question about how do we, going into the future, create new runtimes, tools, and other packages to be able to more effectively manage this kind of data transfer. And so to that end, it seems that there is a bright future for UCX and any sort of data and communication library. Okay, so I believe that's it for my slides. Thank you very much.
Thanks, Matt. And we have here some references if people are interested in reading more about that layer, but that's all we have for today. So thank you very much for listening. And if anyone has any questions, we'll be happy to take them.
Hey, Peter, I have a question. So in one of the slides, you mentioned that UCX is missing UVM. Can you elaborate that? Because current master can support managed memory. Are you talking specific to any other feature?
So we need UVM support for both CUDA IPC and InfiniBand. I think, if I recall correctly, we briefly discussed it.
Yeah. Okay. So you mentioned it's a okay, staging through.
Yeah,
I understood.
Correct.
Yeah, gotcha.
Sorry,
Gotcha.
My explanation was a bit shallow during the presentation.
Yeah, makes sense. Yeah, thank you.
So, Devender, what is the current constraint? Can you please?
So so basically today for managed memory, we cannot do the RDMA operations or even CUDA IPC because the managed memory pages can be moved around to the CPU land or GPU land, basically wherever they get accessed in the latest. So it's the real data source is it's hard to predict. So the RDMA or CUDA IPC can lead to the data validation issues. So for that we need to use the staging protocols. So today we have host-based staging. But if we are sure that the target is the local pair, probably it is efficient to stage it to CUDA memory and map that stage buffer to CUDA IPC and do the IPC transfer instead of going through shared memory or IB path. So the missing part is staging through the CUDA buffers. So that is something currently we are in the direction.
Okay. Do we have when do we expect to have this? What UCX version? Do you have an idea?
Most likely, it should be in the master end of this year or in January timeframe.
Oh, perfect. That's great. It's certainly a feature that everyone would be happy about.
Yeah, this should fix some of these T4 limitations where we have a limited amount of memory can register. So it should solve many other issues as well.
Yeah, that would be awesome. Thanks, Devin.
On that note, I have a question for AMD folks. Do you guys also support CUDA, or sorry, IPC communication between GPUs when the memory is managed, and the same question about RDMA support.
So for managed memory, RDMA support is there. IPC is not supported, if I remember correctly.
Okay.
So when you said RDMA is there, the peer memory module will track the pages and move to either how exactly?
So I don't know exactly how it is being handled by the driver. What I tested was that it can pin the like you can register the memory with IB and do the transfers, and it's able to correctly transfer the data after the data has been touched from either the GPU or the CPU. I'm not exactly sure how the internal driver internally handles it.
Will any special care need to happen in UCX if you're using data that's spilled from GPU to host to transfer, or sorry, when data is spilled from device to host using UVM, will UCX transfer the spilled data, or will it move the data back to device to then transfer it?
So today it uses this staging. So it rely on the CUDA copy, so which basically gets the pages to the GPU and then copies done the copy.
So Ben, to your question, if data is spilled to host, then data will be moved to a bounce buffer that resides on the GPU. So there is this additional work that's done.
Okay. Is that something that's tunable in the future?
Can you elaborate on that? You mean to not move it back, but to rather report to user that the data has spilled and the user decides to move directly from host or something like that? Yeah,
that rather than moving to GPU and then transferring, you could just move from host to host.
I think today there is no GPU API to detect the location of specific ranges as to where they reside. If anything, there's the opposite direction where user can provide hints or some directives to say this memory should reside mostly on the GPU or mostly on the CPU, and that's part of what we've decided to do, which is when we decide to move memory, we basically look at the memory attributes and see if it's mostly CPU or mostly GPU, and we'll make a decision of whether to stage it on GPU buffers or to stage it on CPU buffers, depending on that affinity that the user mentioned.
Okay. Thank you.